In this video, we'll take a look at LSTM, a type of neural network that overcomes the long-term dependency problem in RNNs, allowing it to handle long sequences beyond the limitations of short-term memory. First, let's look at how weights are updated through training in a vanilla RNN. In an RNN, the hidden state from time step, t minus 2, is passed to t minus 1, and then to time step t. In other words, the previous hidden state is continuously passed to the next step, making it a sequential neural network where past information influences the current output. During training, errors between predictions and actual values are computed, differentiated with respect to the weights, and used to update the weights via the learning rate, enabling the model to learn gradually. Let's take a closer look at how weights are updated. In a vanilla RNN, hidden states are passed sequentially across time steps. For example, H1 is passed to H2, H2 to H3, and finally, Y3 is output. Based on the output from the RNN and the actual value, the error E3 is calculated. Using this error, we need to compute the partial derivative with respect to the weight omega xh. Since the same weights are shared across all time steps in an RNN, the total derivative is expressed as the sum of contributions from each time step, 1, 2, and 3. As explained in the previous backpropagation video, this process unfolds via the chain rule, and the gradient at each time step is obtained by tracing back through the previous hidden states. Therefore, in a vanilla RNN, derivatives are multiplied repeatedly along the time axis due to the chain rule, which works well for short sequences. However, vanilla RNNs have several limitations. In RNNs, the tanh function is commonly used as the activation function, and when the hidden state is partially differentiated, the result unfolds according to this formula. That is, while tanh outputs values between -1 and 1, its derivative produces values between 0 and 1. Therefore, in vanilla RNNs, when the sequence becomes very long, the repeated multiplication of derivatives in the hidden layers causes them to converge towards 0, leading to the gradient vanishing problem. Consequently, the weights are barely updated, and information from the distant past fails to influence the current learning, causing the long-term dependency problem. Additionally, examining the partial derivative of the hidden state reveals the recurrent weight, omega HH, between hidden layers. In a vanilla RNN, this same weight, omega HH, is multiplied repeatedly at every time step during training. If the omega HH exceeds 1, the gradients can grow exponentially, potentially causing the gradient exploding problem. To overcome these limitations of RNNs, the long short-term memory LSTM algorithm was proposed. As explained in the previous slide, a vanilla RNN is a sequential neural network in which the hidden state from the previous time step is continuously passed to the next, allowing past information to influence the current output. LSTM, a variant of RNN, incorporates a cell state to maintain information over extended time spans and utilizes gate mechanisms to regulate the processes of forgetting, storing, and outputting information. This architecture effectively mitigates the long-term dependency problem inherent in RNN. Let's take a closer look at the structure of LSTM. LSTM consists of three main components: the cell state, gates, and hidden state. First, the cell state is a long-term memory, updating past and new information under gate control. Through the forget, input, and output gates, LSTM selectively decides which information to forget, store, or output. Each gate passes through a sigmoid function to produce values between 0 and 1, controlling how much information is reflected. Each gate also has its own parameters and operates independently. Finally, the hidden state serves short-term memory at the current time step, summarizing and conveying the present context. In summary, LSTM maintains long-term memory through the cell state and conveys short-term context via the hidden state. Let's look at this in a more formulaic way. The three gates, forget, input, and output, can be expressed mathematically. First, the forget gate is used to discard unnecessary information from the previous cell state. The forget gate, ft, is calculated as follows. The current input, xt, is multiplied by its corresponding weight. The previous hidden state, h at -1, is multiplied by its weight, and a bias is added. The result is passed through a sigmoid function, producing a value between 0 and 1. This value, aft, is then multiplied by the previous cell state, c, to -1 to determine which information to forget. The input gate determines how much of the current information is retained in the cell state. The input gate, HIT, is calculated as follows. The current input, xt, is multiplied by its corresponding weight. The previous hidden state, ht-1, is multiplied by its weight, and a bias is added. The result is passed through a sigmoid function, producing a value between 0 and 1. This value, IT, is then multiplied by the candidate cell state GT to determine the new information to be stored in the cell state. The output gate determines how much of the current cell state should be reflected in the hidden state. The output gate, denoted as OT, is calculated by multiplying the current input xt by its corresponding weight, adding the previous hidden state ht-1 multiplied by its weight, and then adding a bias term. A sigmoid function is applied to this result, producing a value between 0 and 1. This value, OT, is then multiplied by the cell state CT, after passing it through a tanh function, which gives the final hidden state HT. In other words, the output gate controls how much information from the cell state is exposed to the outside. The candidate cell state, denoted as GT, is a value created by combining the current input, XT, with the previous hidden state, HT-1. It represents potential information that could be added to the cell state. However, whether this information actually makes it into the cell state depends on the input gate. The candidate cell state can either be incorporated or ignored, which is why it's called a candidate. Mathematically, it's computed by multiplying the current input, xt, by its weight, multiplying the previous hidden state, t-1 by its weight, adding a bias term, and then passing the result through a tanh function. This is similar to how hidden states are calculated in a standard RNN. The cell state is the core structure in an LSTM that maintains long-term memory. It gets updated by first removing unnecessary information from the previous cell state through the forget gate, and then adding new information extracted from the current input via the input gate. Mathematically, the current cell state is calculated by adding two components: the previous cell state multiplied by the forget gate, representing past information, and the candidate cell state multiplied by the input gate, representing new information. For example, if the forget gate outputs 0, all of the previous cell state is discarded. If it's 1, it's fully retained. and if it's 0.3, only 30% is carried over. Similarly, if the input gate outputs 0, no new information is added. If it's 1, all new information is added. And if it's 0.2, only 20% of the new information is incorporated. The output gate controls how much of the current cell state, CT, is reflected, updating the hidden state, HT. Specifically, the cell state is first passed through a TNH function to scale its values between -1 and 1, and then multiplied by the output gate value to get the final hidden state. For example, if the cell state is 0, none of its information is passed to the hidden state. If it's 1, the information passes through TNH and is fully reflected in the hidden state. If it's 0.2, only about 20% of the cell state information is passed to the hidden state. To summarize, the hidden state, HT, is calculated through the following process. First, based on the current input xt and the previous hidden state ht minus 1, the forget gate, input gate, output gate, and candidate cell state are computed. Using these values, the cell state at the current time step, CT, is updated. Finally, the hidden state is obtained by multiplying the output gate with TNH CT, and this hidden state is then passed on to the next time step,